So what can I say? LFCS is so wonderful. There's no way I can begin to tackle the kind of influence that LFCS has had on me, let alone on the rest of the world. So I'm not going to try. I'm just going to pick out a few papers that come from here that I really like and tell you a little bit about them. And this is especially aimed at the students in the... Who is a student here? Right, so good for you. This is especially aimed at the students and younger people in the audience, maybe some of whom don't know about these papers. And I apologize, this is an idiosyncratic selection. I don't have things like call by value, call by name, and the lambda calculus, which really belongs there, but you get in there anyway, Gordon. I'm going to start with Burstall, MacQueen, and Sannella's paper on hope. How many of you know this paper? Okay. How many of you know a little bit about functional programming? Right. So all of you who didn't raise your hand the first time and raised your hand the second time, you really do know all the ideas in this paper. You just didn't realize where they came from. And something that's near and dear to my heart is tracing the ideas back to where they come from. It's always worth reading the original papers. So those of you who are interested in functional programming at all and haven't read this, I encourage you to go and do so. So this paper is the source, so there it is. And you notice it's from 1980, which is before LFCS was founded, but hey, we can count it as part of LFCS anyway, because Bob Boyer Memorial Society was going then, so it was really LFCS. We're using a loose definition of LFCS here. So one of the things in the paper is, oh look, pattern matching. Now pattern matching didn't start with this paper, but it did start with this line of work. It's Rod. Is Rod still here? No. But it's Rod that we all have to thank for this style of pattern matching. It's so basic. I just took it as mother's milk. Of course you have pattern matching. No, somebody came up with that. That was Rod. That was huge. And I said this talk was addressed to the students here. All of you are capable of doing that sort of huge thing. And you're much more capable of doing it if you realize that, yeah, there are huge things to be done, and actually, it could be me who does them. So a big part of this talk is you've been hearing about all sorts of great work that's been done in this institution to which you belong. Take that as a motivation for where you should be going and where we expect you to be going. The other amazing thing in this paper, and this was the paper that introduced it, was they did the data declaration. And the data declaration shows the type tree of alpha. Alpha is a type variable, and it's either an empty tree, or it's a tip, which contains an alpha, or it's a node, which contains a pair of trees of alpha. So again, this is now mother's milk to us, but it came from this paper. So the really big, huge things come from people. It's amazing. And I'll skip over that because we want to go quickly. So my next choice is Harper, Honsell, and Plotkin's paper, A Logical Framework. And again, there's the paper. And this did appear after LFCS was founded. And it just has a couple of type rules in it. I deliberately put them small so as not to scare you. It's actually pretty compact. This is all of the rules. I mean, there are quite a few different kinds of judgments, right? 1, 2, 3, 4, 5 different kinds of judgments. But then this is actually all the rules. So it's not too bad. It can get worse, right? The formal definition of ML had lots of rules. There was this thing they were working on around the turn of the millennium called ML 2000. And we thought it was named for the time. Somebody said, no, that's the number of proof rules in it. I was told Bob Harper was not amused by that. But here's LF, and this was a system of rules for defining other systems of rules. And here's an example of the kind of system of rules you might want to define. Here is just a tiny fragment of natural deduction. If you go back, again, I'm saying go back and look at the original papers. So go back and look at Genson's original paper, and you will see exactly this. Genson is, by the way, somebody who was great, but was actually not part of LFCS. And what I want to draw your attention to here was the footnotes. So here's the all introduction rule. Any of you who's familiar with logic will know this rule. It says, say you can prove phi of x, some formula phi that contains a free individual x, then for all x, phi of x follows. But it only follows if the footnote holds, and this is provided that x is not free in any assumption on which phi depends. So that is, if no assumptions mention x, and you can prove phi from that, then you're not assuming anything about x, so it's true for every x. Fairly straightforward. Okay, so pay attention to that footnote. So then you encode a logic with a signature. Here's a signature for something a little bit bigger than the logic I just showed you. But then here's the payoff, and this is the bit I wanted to show you. So using a signature like that one, this is the encoding of this rule. And the other one is the encoding of this rule, which also has a side condition. And the really cool thing I want to mention that always stuck with me after having read this paper was that rule has no side condition. Just by abstracting out and turning the inference rules into various appropriate higher order functions, the need for expressing a side condition went away. It became built in. And I thought, that is really an amazing insight. Isn't that cool? Logic's been around for a long time, but here's something, again, new and fundamental that has been found out about logic. So I was amazed by that, Gordon. Were you proud of that when you found that? Well, you should have been proud. Okay, so that's the second one. The third one, nobody will be surprised I'm mentioning. It's been mentioned several times today. It's Eugenio Moggi's work on monads. And here's the very first one from 1988, which was just one of these green tech reports. And I picked the green tech report for a reason, because, well, let's see. I mean, it's got the monad laws in it, drawn out neatly. That's nice. It had more complicated things. I skipped over those very quickly. No, actually, no, I spent hours poring over them, trying to understand that, and I finally managed to. So, if the stuff is scary, don't worry, just keep at it. You'll get there eventually. I loved these bits. It had these lovely tables which had bits of syntactic rules on the left and their corresponding semantics on the right, and you could see very clearly how the type rules and the semantics related. It was a very nice way of presenting things. I tried to emulate that later on. And then it had a reduction system for explaining how the monadic meta-language worked. And it had things like, the obvious rule, if you let x be e in x, well, that's the same as e. And then if you have, this is the associative law, which says that if you've got two lets in a certain order, you can reduce them to another order. And then if you have let x be a value in e, then you can just substitute it out. And then these two rules, which were for introducing lets, and this rule says that if you have, can I read that? Anyhow, this just says that the function to be applied, you just set that to a variable, and then this is the argument. And again, you can bind that to a variable once this has already been bound to variable. So that caught order of evaluation. And these were also expressed as reduction rules. And the reason I put up the tech report rather than the later thing in the Licks proceedings or the later still journal article is because, interestingly, this appeared in the tech report nowhere else. But later, I and many other people built upon this. I see Peter Thiemann nodding, because he and I are co-authors of a paper that builds on this idea. So again, this is a really good reason to go back to the original sources. Sometimes there are gems hidden in the tech report that for some reason never made it into the other published stuff. And you've heard many people talk about the great influence that this work has had. Peter, for instance, has done amazing things with it.
Did Eugenio say why that wasn't in the journal paper?
I'm not, if I ever asked him, I can't recall. I think he sort of said, oh, I didn't think it was interesting enough.
Oh, okay.
So there was an equational version, but this reduction version wasn't there.
Sometimes stuff disappears because it's wrong.
This is not wrong. So nobody will be surprised that my list of favorites includes the pi calculus, which of course had a very small definition. I can't even get it to fill up the page. Right? And it's this level of conciseness and elegance, of course, that we should all be aspiring to. Right? That this is the brilliant idea that Robin and others have had, which is you can take important aspects of the real world and model them with really very simple calculi. Right? And that's a deep and profound idea. And the other half of this, which was made very explicit in Robin's document on is computing and experimental science, and which was already alluded to even by Gordon this morning, is theory, practice, talk. Right? That communication has been at the core of LFCS, and I think is at the core of what we should aspire to. This is the core of how LFCS inspires all of us to do amazing things. I'm glad to see people around the room nodding. And then he had reduction rules very nicely expressed graphically. So you can, so that was just the syntax expressed neatly, but you could also very neatly express how processes evolve over time. And one of the really neat things about this paper, right, the way in which pi calculus was a huge step over things like CS and CSP that had preceded it, is it was powerful enough that you could encode the lambda calculus in it. So here again is the encoding of lambda calculus into pi calculus. This happens to be the linear variant, but then they go on and do the full lambda calculus. And again, there are lots of lessons to be drawn here. Right? So lambda calculus is another old, small, compact calculus that turns out to model many things of great utility. And here's a translation that's compositional from one system into another system. And pretty much in programming languages, everything we do is defining and looking at the properties of such translations. This is what compiling is, right? Taking your source language, expressed as one language, into your target language, which might be a machine language or something else, and then proving that the meanings are preserved. So a lot of what we do is looking not just at interesting core languages, but looking at several of them and the relationships between them. And the fact that this was powerful enough to express lambda calculus was a huge step forward. Before that, the power of these process calculi had been closer to finite state machines. Now this was expanded to anything in the computational realm because, of course, lambda calculus is as powerful as a Turing machine. Note, of course, that this embedding always tells you something interesting. It tells you the system you're embedding in is at least as powerful, possibly more powerful, than the thing that you're starting from. So it tells us that process calculus, pi calculus in particular, is more powerful than lambda calculus, but not the other way. Of course, you'd need a mapping the other way to get that. So it's telling us that processes can model lambda, but this isn't saying anything, just the fact that processes can model lambda wouldn't, for instance, tell us anything about lambda calculus being concurrent. It says you can use concurrency to implement lambda calculus, but it's not saying anything about lambda calculus being concurrent itself. I'll come back to that. So now we move on to another set of papers. So this is actually two papers I'm going to wedge together. So this is Sampson's paper on proofs as processes, which Phil has already talked about. And it inspired, as Phil mentioned, so I wanted to just show you. So this is the beginning of the paper. And then the very next paragraph, this is the very next paragraph, he gives a very nice description of Curry-Howard. And I always admired Sampson, right? He didn't let the normal niceties of prose constrain him, right? He just burst out, right? So in this paradigm, we have the correspondences. They stopped using words. He used a table, right? Formulas as types, proofs as functional programs, normalization of proofs as computation. And then he went on and immediately illustrated it with the formula. So it's very neatly put, very pretty. And he had these nice diagrams explaining the computational interpretation of things like the cut rule. This made a big impression on me. And then the details of that work were then filled out in this paper by Bellin and Scott. And by the way, Sampson did all this just before moving to LFCS, but I'm going to claim it for this talk anyway. And then gave these various rules. So here's the rule for tensor, and here is the rule for par. And we will see these rules again. I will come back to these. This is the wrong bloody version. Shit. Okay. What am I going to do here? Right. I'm going to just go with the wrong version. Sorry with the version editing problem. I thought this had been fixed. But there's one other paper that I put in the later version, which is not here. So you'll just have to imagine it for yourself. This is by Kohei Honda, Martin Kubo, and Vasco Vasconcelos. And it's the paper that introduced session types. And that appeared in 1998, not long after this other work. And session types, so yes, tell Nobuku that Kohei is very well loved here. So session types came along. And then a bit later, I've not cited the paper here because I think it's not one we can claim for LFCS, but Frank Fenning and Louis Karras. So at the beginning, let me back up for a moment. At the beginning, when Kohei did, well, Girard did linear logic, also not something we can claim quite. And from the beginning, it was clear this has something to do with parallelism. I should go back for a minute. Right, so this is an encoding, right? It's again in a tabular form like Moggi's. Here are rules of linear logic, and here's their semantics expressed as a term in pi calculus. And the paper was called Proofs as Processes. And it says, look, linear logic is telling us something, it's expressing concurrency. Well, wait a minute. We saw that Milner had embedded lambda calculus into pi calculus, but that didn't mean that lambda calculus was actually about concurrency. And indeed, here, the fact that you could do this, if you looked at what was going on with the proofs, there were never any races, there were never any deadlocks, none of the interesting stuff that you get in concurrency. Nothing actually ran in parallel. It was all going sequentially, just like an interpretation of lambda calculus, really. So although it was claimed that this was telling us something interesting about concurrency, I didn't quite believe it. I was sad because all of us, from the beginning, including Gerard, thought, right, here, finally, is the connection between logic and concurrency that we'd been looking for. Right? You've got this great thing, propositions as types, which tells you that natural deduction on the one hand and lambda calculus on the other hand are really exactly the same thing. And lambda calculus forms a canonical basis for what we do in functional languages. Now come to the concurrent world. Pi calculus is pretty cool, but maybe it can't quite claim to be canonical. And there are an awful lot of other things around, right? There's join calculus, there's ambience, there's CCS, there's CSP. There are quite a few of them. So it'd be nice to know which is the canonical one. And maybe logic, if there was some correspondence between logic and some way of dealing with concurrency, that would give us the answer. So this is what we were all hoping for. I'm pretty sure it's what Samson was hoping for. Samson's still here. He's gone away. Damn. So he's gone away, right? I can just assert it's what he was hoping for. And certainly what I was hoping for, but I felt this didn't quite get there. Yes, it was a relationship, but wasn't actually telling you anything interesting about concurrency. Damn. Meanwhile, oops. Right, no, we're not there yet. Here, we'll just stay looking at this for a minute. So meanwhile, Kohei comes along. He does session types. Session types are about concurrency. They build on linear logic a bit. So they have a linear sort of system. They have the operators with and plus from linear logic. But they don't have times and par. But they do have send and receive of messages. So a bit of linear logic came through, but then there was this other stuff with send and receive just sort of hacked on the top. And other important parts of linear logic, like tensor and par, weren't there. Then along come, so Kohei's work was 94, 98. This work was 94-ish. Wait a while. That's another lesson for all of you, right? How do you make progress in a difficult subject? Wait a while. So wait 15 years, and come 2010, Lewis Karras and Frank Fenig publish a paper saying, no, actually, session types are exactly like linear logic. And they gave a very nice correspondence with intuitionistic linear logic. And I looked at what they did, and I remembered the work of Samson and the work of Phil and Bellin. I went, this is great. This is what I've been waiting for, and I think I know how to make it better. So that's what propositions as sessions was. And by the way, I spent a long time trying to think of a title for this paper. Right? I wanted to call it Proofs as Processes, but I couldn't because it had been used. And finally I realized that just by going to a different level in that correspondence, talking about propositions now not as types but as session types, and that was where my title came from.
Phil?
Yes?
Do you have any idea why it couldn't be done before and it took 15 years to rethink?
Yeah, let me explain what was done, and then I will give my answer to exactly that question. So there's the beginning of my paper, and mentioning very explicitly, right, the first line of the abstract refers to Abramsky, Bellin, and Scott, and Karras and Fenig, and the next line refers to Honda, and it also refers to Gay and Vasconcelos. And this is more advice to the people in the audience. You often think when you're a young person just getting started, I've got to make a name for myself. I have to show what's unique and important about my work. And as a result, very often your related work section just mentions everything else you know about and says something awful about it. Right? Don't do that. Right? As Tony Hoare says, the best way to deal with your colleagues and rivals is to praise them to the hilt. And frankly, they deserve it. So anytime you have a chance to say something good about a colleague's work, anytime you have a chance to point out that you are building on a colleague's work, seize it with both hands. We are all working together as a community. This, again, of course, is something that's come out through the day that LFCS developed. Everybody worked together as a community. And we are all working together as a community. So when you build on somebody's work, say that's what they're doing. When somebody else has done something great, seize on it, make it your own, but acknowledge the source and praise them. Because they deserve it. And you deserve it too. I was very far along in my career before I finally started to do that. And then when I did, I went, ooh, this feels good. I like this. But it took me quite a while to get there. So maybe you can get there more quickly. And you notice that for my introduction, I stole Sampson's way of presenting things. Right? My only difference was my way of doing it was more colorful. So here's the key bit of the paper. I'm just going to focus on the formulas. So this is those two rules that we saw copied out from Bellin and Scott's paper, just in slightly different notation. And the key thing that they said is, okay, say you've got a process P, it's got a bunch of channels, let's call those gamma, and it's got one channel Y, and that's behaving according to the linear type A. And then Q has a bunch of channels delta and one special channel Z that's behaving according to the linear type B. Then we're going to form, right, we're going to restrict over Y and Z, so we'll do a nu over Y and Z, and then X gets sent a YZ pair. So they're using a variant of the pi calculus where you can transmit pairs. And then in parallel, we'll run P and Q. And then we'll say, what's the type of the channel X? Well, it's a pair of an A and a B. And then par was something very similar. It receives. So this sends an YZ pair, and this receives a YZ pair along the channel X. And this is my reformulation of what Bellin and Scott had done, what Sampson had done, and what Karras and Pfennig had done, which was to recognize, right, and the insight here was not mine, right, the insight here was Karras and Pfennig's, that if you just rename things a bit, it looks like a session type. So this is formally just the same, except instead of sending X a YZ pair, we send X a Y. Wait a minute, what happened to Z? Oh, we're calling Z X. So what this says is, what is the behavior of channel X? It's going to receive something of type A, and then after that and then P is going to provide that A, and then after that, within Q, X behaves as B. So it's send an A and then behave as B. And this one becomes receive an A and then behave as B. So we've now added some sequentiality here. And all of a sudden, these look like the send and receive of session types. So Kohei had just said, oh yeah, this bit of linear logic, with and plus, I'll take that. That's about making choices. And then send and receive, I will hack on the top. 15 years later, it's finally recognized, no, you don't need to hack send and receive on the top. Furio. You don't need to hack those on the top. They were there all along. That's actually what tensor and par were, which is an amazing insight. And I hadn't even realized how amazing it was until after I wrote this paper. I met with Louis Karras, and he told me this story about, isn't it amazing that It was there all along, and Kohei hadn't seen it. And none of us saw it for 15 years. And now you ask, why was it so hard to see? Well, the reason it's hard to see is, remember the interpretation is send an A and then behave as B. So it's asymmetric. And we're used to thinking of tensor and par as symmetric operators. You need to think of them. Are we allowed to think of them asymmetrically? They're symmetric. Yeah, it's fine. It's just like Cartesian product. The Cartesian product of A and B might be, say A is number and B is string. It might be the pair 1 high. If you confuse that with the pair high 1, you'd be in trouble. Right? The order is very important in a pair, but there's a symmetry. It turns out there's still a symmetry here. There is a process you can write that turns an A tensor B pair into a B tensor A pair and then goes back. So we've got the symmetry that we need. But it was just this simple thing of, oh, it's supposed to be symmetric and you need to view it as asymmetric. That's what took so long, I think. No proof, but that's what I think made it difficult. So very easy things can make things very difficult. So let me wrap up. I said I was addressing the young people in the audience. Now, hearing about all the fantastic work that's done today, you might think, damn, I'm too late. They've done all the good stuff. They've already found pattern matching and data types and even how to do session types. And they've almost got a propositions as types correspondence that tells us something about concurrency. So, isn't that awful? I could have done great stuff, but all the people have come and they've done it already. Oh, come on, guys. Physics has been around since Newton, hundreds of years, and they're still finding interesting stuff. Computing has been around only since Turing. There is plenty left for you to do. I am sure that there is stuff as fundamental as pattern matching, as fundamental as data types, as fundamental as the pi calculus, just waiting for you to find it. And all you will need to do to find it is not be as stupid as your elders. Not be like the elders who were saying, oh, wait, it's tensor, it must be symmetric. And just realize, oh no, I can look at it asymmetrically. There are all sorts of things like that waiting for you to discover them. You will be the next generation of Milner, of Burstall, of Plotkin. Go to it, guys. I'm really looking forward to seeing it. I bet we all want to go get a beer.